Alright guys, so just a quick reminder before we start in on this video of what we talked about last week. This is page 28 in your packet. We talked about exponential models. Exponential models being ones where we either are multiplying by the same thing each time or dividing by the same thing each time. And they take the general format f of x equals a times b to the x power, where a is the initial value, however much you start with, and b is either the growth factor if your numbers are getting bigger or the decay factor if your numbers are getting smaller. Growth is if you're multiplying by the same thing each time. Decay is if you're dividing by the same thing each time. So if we take number 1, for example, we first of all know that our initial value always matches up with 0. So our initial value is -5. And then in this case, it's going to be growth, because if we look at the absolute value of those numbers, they're getting bigger each time. So if we ignore the fact that they're negative. And we are multiplying by 4 each time. It's important that we don't call this the rate of change. Rate of change, remember, is specific to linear functions. And so my growth factor is 4, because that's what I'm multiplying by each time. So my function is going to be f of x equals my initial value times my growth factor raised to the x power. So that's my model. So first, before we move on to our next example, just need to show off a new trick that I found out. Whoa, it's a lightsaber! May the force be with you! May the math be with you! Okay, anywho, so on this page they ask us to decide if it's linear or exponential. Remember, linear is if you are adding the same thing each time and it takes this form. So linear functions are in the format f of x equals mx plus b, where m is your rate of change and b is your initial value. And then exponential functions, we discussed on the last page, are in the format ab to the x. And that's when you're multiplying or dividing by the same thing each time. So if I look at example 1 right here, that's going to be a linear function because I am subtracting 3 each time. So I'm taking away 3 each time, so that tells me it must be linear. And not forgetting my initial value always matches up with 0. So my equation, making sure I use mx plus b since it's a linear function, is f of x equals my rate of change, -3x, and then plus my initial value, which is -2, so I can simply write -2. The next one I want to draw your attention to is number 12. Never gets old. Obviously, number 12 is not linear because I subtract 4, and then I'd subtract 2, and then I'd subtract 1. So that's not linear because it's not a constant rate of change. And it appears to be that I'm dividing by 2 each time. 8 divided by 2 is 4, 4 divided by 2 is 2, and so on. However, with exponential functions, we always talk about it in terms of multiplication. So this is one of those examples where it's decay, where it's getting smaller. And instead of saying divided by 2, I would simply say that I'm multiplying by 1/2 each time. Dividing by 2 and multiplying by 2 or multiplying by 1/2 are the same thing. So this is exponential. My initial value still matches up with 0. So it's f of x equals 8 times my decay factor is 1/2 raised to the x power. Something exponential functions are really useful for are situations that have a percent increase or a percent decrease. I'll start with a basic example. Let's pretend we have a population in a city of 100 people. If I told you that that population increased by 5% each year, we would know that after the first year, there would be 105 people in that city. Because 5% of 100 is 5, but we still have to account for the 100 people that already lived there. So basically what we did here was we multiplied the initial population 100 by 1.05. The 1 accounts for the 100 people that already lived there. And then the 0.05 was another way of writing 5%. And so, in general, what we're going to do is we're going to take the initial value and multiply it by 1 plus the percentage if it's getting bigger, so if it's growing, or 1 minus the percentage if it's decaying. So the first problem says write an exponential function to model each situation. Find the value of each function after 5 years. So the first problem says that you have a $12,500 car depreciating, which means decreasing by 9% each year. So my function is going to be f of x equals my initial value, 12,500, times, since I'm decreasing by 9%, I want to subtract that from 1. So I'm going to multiply it by 0.92. 0.91, I mean. Because I'm subtracting 9% from 1. And 9% is written as 0.09 to the x power. But they want to know the value after 5 years. So instead of using x, I'm going to replace that with 5. Which, when I put that in my calculator, gives me 7,840 cents. So that's the price of the car after 5 years. The next problem says that a baseball card was bought for $50. So that's how much the baseball card started with. And then it's being increased by 3% each year. So f of x is equal to the initial amount, 50, times, since I'm increasing, I'm going to do 1 plus 3%, which is 1.03, raised to the x power. But since I'm trying to figure out the value after 5 years, I'm going to replace x with 5, which is $57.96. So after 5 years, the cards are going to be worth $57.96. So keep in mind that this value and this value come from taking 1, which represents the whole 100%, and either subtracting the percentage like we did in the first example, or adding the percentage like we did in the second example.